So if we take a look at this problem, you want to do a rewrite, make that a 1/2 power, put a dot between them. You have to make sure to do the product rule, okay? So when I did the product rule, here's first times the derivative of the second plus second times the derivative of the first, and then plug in 4, okay? Now, I don't simplify first if I'm going to have to plug in a number. I do just plug in 4 and go for it. So this gives us 11, half is a half. This gives us 1 over the square root of 25. That's why it turns into 1/5. And then 2 times 4 is 8. This gives us the square root of 25, which is 5. And then, you know, many times, just get yourself a common denominator. So that 10, make it 50 over 5. So 44 over 5 plus 50 over 5 is a final answer of 94 over 5. Okay, so that is something that's not going to go away. Remember, the final exam in this class is comprehensive. So I will be reviewing things. That's why I didn't want to move on going backwards until we knew our derivatives very well. So make sure if you're doing stupid mistakes on your derivatives, when I give you back the gateway, then you'll be able to check and see what mistakes you're making. Okay. That being said, today we are going to talk about antiderivatives. So we are going to talk about the most basic general antiderivatives, so allowing us to go backwards. Okay, so we're talking about going backwards. So the backwards is the antiderivative. Now, if you were here, and I think most of you were, that little game we kind of did where we were switching back and forth started giving you the idea of what it's like to go backwards. Okay, so yeah. So let's talk about antiderivatives. We're going to use the notation because the prime notation is what we use when we are going forward. To go backward, we are going to use capital letters as our notation. So if we start out with a little f, so we have little f, and if we want to go backwards, we're going to call it capital F. So you'll notice that it's capital F. Now, we put this plus C here. Now, we didn't do that when we were doing that little game to get started, but we put that plus C here to say, hey, there could have been a constant there, right? What is the derivative of 7? 0. What is the derivative of 10? 0. So when we go backwards, we have to account for the fact, hey, there could have been a constant there. And so that's why we put the plus C. So anytime we are doing an antiderivative from now on, we've got to put a capital plus C. Now that just means there could have been a constant there that was deleted in the process of deriving, so we put it there to account for that. Because think about if we got a function's derivative was 2x, was the original function 2x plus 4, 2x plus 7, 2x plus 10, 2x, or x squared plus 2, x squared plus 4, x squared plus 7, who knows? So we have to account for that, and so we account for that constant with a plus C. Now there are some applications where sometimes they give us enough information that we can find out what that constant was, and we will talk about how to find that constant when necessary. But that's the notation we're going to use, okay? So to find the most general antiderivative of the following, okay? So we have to ask ourselves, whose derivative is a sine? Well, it's almost a cosine, but not quite. What's it missing? A negative. So it would be a negative cosine plus C. There could have been a constant there. So what's interesting, when we take a derivative, all of the cos get a negative tacked on. When we take an antiderivative, all of the trig functions that don't have a co in front, so like sine, tangent, and secant, they have to get a negative attached to them. So all of the things that we antiderive that came from a co, like this one, you will notice that it changes sign, okay? Now, here's an interesting one. For part C here, I skipped a B, don't worry about it. I think it might have had to do with e's and natural logs at the time, but anyway. For this one, if we want to think about if we have something with a power there, for a derivative, we drop the power down in front and we add to the power. So here, if you think about going, or we subtract 1 from the power, here we would have to add to the power and divide by that original power. So divide by the new power. So our antiderivative for a power function is always add 1 to the power and divide by that original power. Now we have to have the plus c because there could have been a constant there that we just are unaware of. But this gives us a general rule for going backwards for any power function. Example, let's say that our function was x to the third. Its antiderivative is going to be x to the fourth divided by 4. Now we should be able to check any antiderivative. If we take its derivative, we should be able to go backwards. So if we took the derivative of this, we would get 4x to the third divided by 4. Do we get this function right here? We sure do. Okay. Yeah, so normally think about the fact we would multiply and go down by 1. Now we divide and go up by 1. Okay, so it's just reversing that process. So everything we know is we're just reversing that process. So there's going to be some rules we got to think about when we are now reversing our process. So here are some rules for you. Don't worry about if there's a constant in front, just like if there's a constant when we derive, when we antiderivative, the constant just sticks along for the ride. Don't worry if you're adding 2 functions, just evaluate each thing separately like we would for a derivative. Here's the rule we just now found for power functions. Sine becomes a negative cosine. Secant squared becomes a tangent. Secant tangent becomes a secant. Cosine becomes a sine. So those are the 4 trig functions that are used most often. So you're going to definitely need to know your power function reversal. Cosine becomes a sine, sine becomes a negative cosine, secant squared becomes a tangent, secant tangent becomes a secant. Now the reason they call it particular antiderivative, that's because you'll notice they didn't write the plus c each time. So that would be like if the constant originally was a 0. There was no constant. So they're just trying to show you the rules. So those are some rules that you're going to need to know. You need to know how to go forward. You need to know how to go backwards now. Okay, so we're going to need to know both directions. So let's take a look at example 2. So they've said that g prime is 4 sine of x plus 2x to the 5th minus the square root of x all divided by x. Find g. What would be our original function? Okay. Now see where it says to find all functions. That means make sure to put the plus c on there to account for any individual constant that could have popped up. Now, just like when we were doing derivatives and rewrites were helpful, for antiderivatives, rewrites are going to be helpful. So let's do a rewrite to this before we do anything else. Okay. So if we're dividing by a monomial, let's just actually divide it. So we would get 2x to the 4th. Now, this is x to the 1/2. If the bases are like when we're dividing, we subtract the exponents. So 1 from 1/2 is negative 1/2. So it's technically that. So I have not done an antiderivative yet. I just did a rewrite, so I can. Okay. So now we're going to go backwards. So what's the antiderivative of a sine. How did it start to be? What would it have started with? Well, it would have been a cosine without the negative is absent, so you got to put a negative on there. 2x to the fourth. To go backwards, we have to add 1 to the power and then divide by that original power. Here, we've got to add 1 to the power, divide by that original power. And then, because it said all functions, we're going to put a plus c. Now, let's make this a little prettier. So it's negative 4 cosine of x plus 2/5 x to the 5th minus 2x to the 1/2 plus c. Now, the way to check a antiderivative is with a derivative. Think about if we were checking a multiplication, we could use division. If we were checking a division, we could use multiplication. Does it go back to the way it starts? To divide by 1/2 is the same as multiplying by 2. Just you would multiply by 2 over 1, which is 2. Okay. So let's do a little check. Did it work? Okay. So the derivative of negative 4 cosine of x is positive 4 sine of x. That part worked. That's good. The derivative of 2/5 x to the 5th is the 5 would drop down in front, so it would just be 2, and then it would be x to the 4th. If I take the derivative of negative 2x to the 1/2, it would be negative x to the negative 1/2. And then the plus c would be plus 0. Look, it matches this perfectly. It might not match this one unless you rewrote it one more time, but it should match your particular rewrite that you did to get it ready, okay? So you can check an antiderivative by doing a derivative, okay? It should work out to be what's on the page. Everybody good with example 2? Okay. Now, calculus became a thing because of the motion of the planets, and that is called rectilinear motion. A weird name, but the thing that we need to remember, okay, let me first go backwards. If I start with the position function, then if I take the first derivative, I get the velocity. If I do it again, I get the acceleration. So if I go backwards, I get from acceleration to velocity. If I go backwards one more time, I get to position. So we know the acceleration of gravity, that negative 32 feet per second squared, or what is it, negative 9.8 meters per second squared. I don't know. It's been a long time since I took physics, but good old Newton was able to take what he knew about gravity and work backwards. And he could then find a position function for a planet, an orbit of things that up until that time they could not predict. I believe the story goes that have you heard of Halley's Comet? Every 70-something years it comes back around. I don't know, but Newton and Halley were friends. Halley's like, I know this comet's coming back around. I need an equation. I need a math to prove it. And Newton, being the genius that he was able to work his way backwards and find the equation for its motion. And it stems a lot from this. And just think about being able to come up with these formulas in your head, kind of amazing. But we need to know that the antiderivative of the acceleration will go backwards to velocity, go backwards one more time to position. Sometimes you will need to know those initial values. Sometimes they will say S of 0, or they will put a little 0 notation next to it, sub 0. And so, same thing here. V of 0 is sometimes written as V at the initial spot, V of sub 0. So it depends on the book and the notation. Sometimes we'll see some that write it both ways. Okay, so we practice a little bit. If you take the derivative of the position, we get the velocity, and then we do it again, we get the acceleration. So now here's an application of how we go backwards. So you just have to know that now we can go backwards. And so it becomes something that's really helpful. Okay. So that being said, let's look at an example. So we know a particle that's moving in this a sub t. It's moving in a straight line, and it has an acceleration function of 6t plus 4. Its initial velocity is -6. Its initial position is 9. Find its position function. Okay, so I know the acceleration of this particle is 6t plus 4. Okay, I'm going to go backwards one step, and I'm going to find its velocity. So v sub t is going to be 6t squared divided by 2. I'll just write that as 3t squared. 4t plus the constant, which is the initial velocity. Okay. Now, they told us that at time 0, we are at -6. So that means that our initial velocity is -6. So let's go ahead and put -6 right there. Okay, so now we have this particle's velocity function. But I want its position function because I want to find its position at any particular time in space. So I need to go backwards one more time. So now I'm going to do the now I'm going to do the position function. Okay. So now we're going to do the antiderivative one more time. So now it would be 3t to the third divided by 3. So the 3's cancel out. This would be 4t squared divided by 2, or 2t squared. And this is going to be 6t. And then this is going to be plus the initial position. That's our constant. Now, they told us that our initial position was 9. So let's go ahead and put the 9 in. And then we have found the position function. And I'm going to show you how to check your work. Okay? So let's check our work. So if I plug in 0, do I get 9? Yes. Okay, so that's the first thing. That's why that initial position is 9. Okay, because all the other things have t's in it. So if we put in 0, we need that 9 there. Okay. If I take the first derivative, do I get the velocity function? Well, the derivative is 3t squared plus 4t minus 6. Look at our velocity function. It matches. Yay. Okay. Let's do it again. Does the second derivative match our acceleration function? 6t plus 4. Sure does. Matches this one right here. So you can check these very, very quickly to see if you've made a mistake, because the and you could plug in the velocity of 0. You better get -6. That also works. The velocity of 0 does equal -6. So remember, that's your velocity. That's your acceleration. Okay? So it's just in real world times, this was revolutionary at the time. And especially when it comes to the motion of objects. It was very hard we could find an approximate equation, but this allowed them to really it just revolutionized physics at the time. Let's take a look at this one. An object near the surface of the Earth is subject to gravitational force that produces a downward acceleration denoted by g. So the acceleration, because it's downward, we always do want to list it as a negative. For motion close to the ground, we may assume that g is a constant and its value is being about 9.8 meters per second squared or 32 feet per second squared. Now, if you look in the problem, the first thing you want to identify, are they using the metric system or are they using standard system? So they're using feet per second. So what we can say then is that g of t is negative, because it's moving downward, negative 9.8 meters per second squared. Okay. It says a ball is thrown upward with a speed of 48 feet per second. So that means our initial velocity is 48. From the edge of a cliff that is 432 feet from the ground, our initial position is 432 feet. So let me say that again. If I throw it up with a force of some sort, that it's initially starting out at a certain speed, that's our initial velocity. If I'm standing at a certain height, that is the initial position. Okay? So that's what those two pieces of information is telling us. It says, find its height above the ground t seconds later. That's its position function. So they want to know what is the position function. And then we will go to the other parts of the equation from there. When does it reach a maximum height and when does it hit the ground? Okay, so first, we need to go backwards. This is an acceleration, so we can even call it a sub t to kind of fit the notation. Wait, I said something, but I didn't do it, did I? It is feet per second squared. Should I use negative 9.8? No, don't. I need to match units. So how about negative 32 feet per second squared? That matches more. Okay. So we're going to go backwards one step. We're going to find the velocity function for this particular ball that's being thrown. And then we're going to find the position function, and then we'll be able to answer the rest of the questions. Okay. So the velocity function is going to be negative 32t plus the initial velocity. That's the constant that you have to add on for these particular application problems. So our velocity function is negative 32t plus the initial velocity of 48. Okay, so that's our velocity for this particular scenario. Now let's talk about the acceleration. We're going to go backwards again. So we've got to get negative 32t squared divided by 2 is negative 16t squared plus 48t plus our initial position. Oh, I'm sorry. That's position. Plus our initial position. I'm so used to going forward that the first time I do this, and you're going to find it too, you're going to want to go forward instead of backwards. Anyway, so now our position function is given by negative 16t squared plus 48t plus 432. Okay. Now, that is our position function. So it says find its height at t seconds. This is its height at any t seconds. Is the position, the height at any particular time. So the next thing they say is, when does it reach its maximum? Well, there's a few different things we know about maximums. Maximums occur at the first derivative, where the first derivative equals 0. Remember that? That is a thing. The first derivative is our velocity function. So we can just set that equal to 0. This is also a parabolic function, right? It's a parabola. Parabola always occurs at the, if you have a parabola, where does the maximum always occur? At the top, right? At the vertex. So if you know how to find the vertex, you can do it like that. But the maximum, a maximum, we're going to take the first derivative. We know the first derivative is our velocity, negative 32t plus 48. Remember from our derivative applications, a critical number occurs where the first derivative equals 0, or is undefined, but this is always defined. So where does negative 32t plus 48 equal 0? Well, that's negative 32t equals negative 48. So negative 48 over 32, negative 32. You better get a positive time or you did something wrong. Reduce that fraction. That's at 3/2 or at 1.5 seconds. So at 1.5 seconds, we are hitting the maximum, okay? Now, the question was, when does it hit its maximum? Be careful if it says, what is the maximum? You're going to have to put that into your height function. You would put 1.5 into the S of t function. That would be what the maximum height is. And then they said, when does it hit the ground? Well, a function hits the ground when its height's 0, right? So, or thing hits the ground when its height's 0. Here's our height function, our position function. So you're really just asking, where does that equal 0? Now, all of those numbers, they were nice to us, are divisible by 16. So let's divide everything through by negative 16 to make that front number positive. It'll be easier. So we get t squared minus 3t minus 27 equals 0. And that is a factorable quantity, which is awesome, because that's t minus 9 and t. Oh, it isn't factorable. Oh, that's so sad. We're going to have to use the quadratic formula. Ugh. Okay. So it's negative b plus or minus the square root of b squared minus 4 times 1 times negative 27 is 108. All over 2a's, which is 2. The negative version will give you a negative version. So it's just 3 plus the square root of 117 over 2. And you can't go backwards in time, so you can ignore the negative. So it'll hit the ground at 8.4 seconds. The position equals 0, because the other one, that negative, you can disregard. If it's factorable, keep the positive version, not the negative version. So that is an application of this stuff, okay? So that's one of the most important applications that we will be studying. At the higher you get into calculus, the more real-life applications it occurs in science and in business and in things you wouldn't even think of. You do get some applications occurring, okay? Does that kind of make sense? A little bit. Okay. So your job, let's check if I want you to do all the odds 1 to 39. I don't know if we'll do all those. Some of them are just do the antiderivatives. So in the book, in the digital book, if you look for page, let's find the page, page 273 in the corner of your digital book. So I would look somewhere around page 300 in the PDF. The 3.9 exercises, we definitely want to do we want to do all those? We kind of do, but I want to do some of the last ones with you together. I want to do 37 and 39 with you. But I also want to do, please add on there 53. Okay, so I would like to do 37 and 39 with you. Skip 35, skip 35. Okay, so let's do 33, 37, and 39. Okay, so open up your books for me. Find less than 3.9. I'd say it's somewhere, well, the corner of your book should say 273, but it's going to be somewhere around 300 probably in the PDF. We're going to do 33, 37, and 39 together at this time. Okay, so let's do 33. They give us that our second derivative is negative 2 plus 12x minus 12x squared. F of 0 equals 4. F prime of 0 equals 12. So that's the problem for 33. They want us to find f of x. The instructions say to find f. So we're going to go backwards 1. And if we go backwards 1, that would be negative 2x plus 12x squared divided by 2 minus 12x cubed divided by 3 plus our constant. Okay. Now, before we move on to that, we're going to use this information. If I plug in 0, I better get negative 12, right? So I know negative 12 has to be my C. So now I know my first derivative completely is negative 2x plus 6x squared minus 4x cubed minus 12. Okay, so now I know my first derivative. Let's go backwards one more time to find my original function. Everybody see how I got my first derivative, how we went backwards one time. Okay, let's go backwards another time. So that's going to be negative 2x squared divided by 2, which is negative x squared, plus 6x cubed divided by 3, minus 4x cubed divided by 4, minus 12x, plus our c that goes with our f function. You don't have to call it c. Sometimes I'll change the variable name to be just, d now or e and then f. I'll just keep going. And so I didn't use the fact that if I plug in 0, I better get 4. So in this case, 4 should equal c. So 4 should equal c. So f of x is negative x squared plus 2x cubed minus x to the fourth minus 12x plus 4. Does that make sense how we're getting these? So that's 33. Everybody see 33? Do we have any questions about 33? Okay, now we're going to do 35. No, we're skipping 35. Now we're going to do 37. Let's do 37 together. This one is kind of an interesting case, okay? Okay, so let's go backwards 1. So our first derivative will be 4x plus 6x squared divided by 2. So that's going to be 3x squared plus 24x cubed divided by 3, which is 8x cubed plus c. Okay. Now, you'll notice over here, did they tell us anything about our first derivative values? No. So we can't replace our c at this time. Or eventually we're going to get to, but not yet. Okay. Now let's go again. Let's go backwards one more time. So now it's going to be 4x squared divided by 2, 3x cubed divided by 3, 8x to the fourth divided by 4, cx plus d. Here's where you need two variables. Or you can call it C1 and C2. I don't care. Okay.
Wouldn't be the derivative, wouldn't be 2 minus and 7 being just f(x)?
No, we're going backwards, remember? So this became 1 and this became nothing. That came the original. Okay. So now let's use this. If I plug in 0, I better get 3. So if I plug in 0, that's 0, that's 0, that's 0, that's 0, then we just find that D is 3. Okay, so now let's plug in, let's put the 3 there. Okay. Okay. They gave us this on purpose. If I plug in 1, I should get 10. Okay. So I'll get a value of 10 when I plug in 1. So let's plug in 1. I get 2 plus 1 plus 2 plus C plus 3. Do you see how that point is going to give us the C that we didn't know? Okay, because when I plug in 1, I better get 10. So all the x's became 1s. So 2 plus 1 plus 2 plus 3. That is 8. So 10 equals 8 plus C. So C is 2. Now I know my full function. So it's 2x squared plus x cubed plus 2x to the 4th plus 2x plus 3. That is my answer. Now, how could we check that we're right? Well, if you plug in 0 to that, you do get 3. Check. If I plug in 1, I do get 10. Check. If I take the first derivative, I get that because I get 2x squared plus x cubed, or I'm sorry, I get 4x plus 3x squared. You know, if I take the second derivative, I better get that. So you can check your work as you go. These are pretty good to check your final answers because you can do derivatives quicker than you can do antiderivatives. It's like multiplying and dividing. So that's 37. Any questions about 37? Okay, let's do 39. I know you're enjoying this, aren't you? No? Okay. Okay. So we're going to go backwards once. If we go backwards, we get 2x plus the sine of x plus c. Now, this information does not, remember the derivative of the sine is positive cosine. Okay, so be careful when you go backwards a cosine, it does become a positive. We don't have any information to plug in to find the first derivative's c, that's constant, so we just got to leave the c there in the next step. Now let's do the next step. Ooh. So now if we take the antiderivative of that, we get 2x squared divided by 2, which is x squared. This time we get a negative cosine of x plus cx plus d. Okay. If you plug in the 0 value, that's going to be our d, right? Because all of these are 0. So I know d is negative 1. That's what that one tells us. So let's put that in there. Everybody with me there? Now, you can tell we haven't used this. If I plug in pi over 2, I should get 0. If I plug in pi over 2, I should get 0. Okay. So I better get 0. So this is going to be pi over 2 squared minus the cosine of pi over 2 plus c times pi over 2. Okay. Now, cosine of 90 is 0, so that's just 0. So that's going to be pi squared over 4 plus pi over 2 times c. Subtract pi squared over 4. Divide by pi over 2 is the same as multiplying by 2 over pi. So we just got to simplify that, and we've got C. Now, one of the pi's cancels, one of the 2's cancel, so that's negative pi over 2 is equal to C. So our final answer is that f of x equals x squared minus cosine of x minus pi over 2x minus 1. How could we check our work? Well, if we plug in pi over 2, we better get 0. If we plug in 0, we better get negative 1. If we take the first derivative, we should see that. If we take the second derivative, we should see that. So if you follow that, that's the hardest one. Don't forget, please, to add in number 53. Please do number 53, okay? So that is that. Isn't that glorious? Please have this done or mostly done by the time you see me tomorrow.